Well, welcome everyone to our case study webinar series. This is John Sankey. I'm a solutions engineer from True Blue Technologies. It's a sales engineering firm that supports groundwater characterization and remediation technologies such as Aestus, Tersus Environmental, TRS Group, NRX, and West Bay. So this is a series of case study presentations, short case study presentations that really focus on the main topic of managing complex groundwater projects and remediation projects using high-resolution site characterization. So today we're super pleased to have Dr. Todd Hallahan show us how to figure out vertical pathways in Bedrock at NAPL sites using surface geophysics, or what can be called electrical hydrogeology. So Todd's background: Todd is a professor and the Sun Chair of Hydrogeology at Oklahoma State University and serves as the Chief Technical Officer for Aestus. As one of the recent NGWA McElhaney lecturers, Todd gave talks all over the world, which was quite a chore. But anyhow, Todd, so thank you very much for presenting this case study. You now have the lead.
Thanks, John. And in terms of being a chore for getting around the world, it's for the people trying to schedule travel for that, it's a brutal actual thing. But thanks for coming this morning. And I've got a managed conflict of interest. I'm a professor, so I have graduate students do those sorts of things, and I'm a part of a company that came out of the university. So if you got questions about managing conflict of interest and how to do those things and what rules apply, it's essentially if you have the morals of a kindergartner, you're fine. But other people don't have that and have thought of interesting ways to do things. So you have to have one of these agreements, and if you got questions, let me know. And then Stuart is, so I'm in Oklahoma, and Stillwater, Oklahoma. Stuart's in Loveland, Colorado at the Aestus home office. And then John's out in California doing great things for True Blue. In terms of your time, we're going to try to be respectful. So I'm going to try to go 20-25 minutes and wrap it up and do Q&A. If you want to hang out for Q&A, we'll stay and answer questions as long as you want to ask them. There's a question chat box that you can do on the GoToWebinar to do that. And so feel free to stick around if there's questions that want to keep going. It's being recorded, so if you want to listen to it again or see something that you wanted to check, that'll be available, as well as CEU certificates. And then there's a giveaway for, if you're allowed to accept it, a Starbucks or an Amazon.com gift card. And the magical thing will happen and somebody will be notified by the end of the week. So that's that stuff. So for electrical hydrogeology, I spent 20 years looking at the ground and its electrical properties to figure out hydrogeologic conceptual models. So when you start trying to understand it, doing all the things that you do in a standard hydrogeology class or profession of I want to look at water levels, or I want to look at contaminants and their distribution, or I want to look at water supply problems, or this and that. It's, hey, how do I do that electrically? And there's a bunch of different ways. And so we've been working on that research and coming up with these methods for the last 20 years. So what you're going to do is you're going to scan a site, and you're going to scan basically a kilopixel image. So you do that from the surface and get a picture. This is a picture of a sort of a standard karst site, so pretty flat on the top, but there's dolines in the subsurface that are controlling flow and dropping vertically into the subsurface. So you take one of those and you get a couple thousand pictures and a view of some angle relative to the karst features. And then you put that in 3D, figure out some places that you want to test the biopsy and check where the tumors are. And then you build up a conceptual model that you can really find the targets you're looking for, because you've got the data density that you can work with. And so instead of having, 10 or 100 wells, you've got 22,000 data points plus your wells to work with to look around a site. In terms of numbers, and I use dogs in my slides, and so if we want to think about conductive dogs, those are the dirty ones. So clay, but also salt water and microbes. And if you're working with microbial activity, their structures make the ground more conductive, and so you'll actually get the colony structure out of the images as if they're eating something in the subsurface. On the resistive side, if you have nice clean gravel or sands, no fines around, that's nice and resistive, or undegraded fuels or undegraded solvents. So if you don't have the microbial activity kind of growing around those things, they're nice resistors in the subsurface. So if we want to look at vertical flow paths, we're going to look at a couple different options here. First, we're going to think about if you're taking an electrical picture from the surface as a 2D plane, what does that look like when you're looking at a fracture sitting in the subsurface? Then we're going to look at a couple different cases. We're going to look at a uncontaminated case in Oklahoma, a fluid-dominated case in Australia, and then we're going to look at PCE and Stoddard solvents, so both L-NAPL and D-NAPL in a metamorphics case in California. So we've got this, we're going to create this trapezoid of data set. We'll have a couple thousand data points, but we're putting it into a domain where the fractures are sitting at some orientation. And this is, if you've had a structural geology class, this is the strike and dip nightmare and some different concepts about apparent dip and those sorts of things. So if we put that image on there and we go perpendicular to the feature and things, we can get the same angle back and we can see that fracture running through the image. And you can tell those angles within about 5 degrees. And you can see them running through the image and use those as targets. If they're dipping enough, you got to decide, are you wanting to target the top or the bottom if you're using vertical wells. And so you got some tricks to think about if they are dipping too much. If we turn though, we're going to start changing that dip and the fractures become less fracture looking and they start having a little bit of a smear to them and they get the angles changed. And if we go the other direction, we don't have a dipping fracture anymore. We just have a change in the image at a bedding plane. And so you've got to think about that relative to collecting a set of data. If you're in a fractured terrain, you're going to want to think about either, do I already know the dominant fractures in this area, or do I want to take a few different angles and figure out what's really controlling the set of data that I'm working with? So this is Oklahoma's largest spring. If you didn't know, is Bird's Mill Spring. It's a water supply for Ada, Oklahoma, and it's got a lid on the top of it to protect the water supply. So if you're going to do any research in there, you've got 17 degrees C groundwater at a constant temperature year round, and it provides a really nice water supply. But we're using that as a test case for a number of different imaging things, and we're also using it as an enhanced aquifer recharge test site. The city of Ada wants to understand how they can better manage their groundwater using enhanced recharge. So we've been doing a project down there looking at a bunch of faults, and the faults aren't necessarily known. Some are mapped out, but some of them are not, and they want to understand the structure of how water gets to that spring. And we're up on the larger scale. So if we're looking at fractured sites, this is a football field for scale. These are your regional scale kind of evaluation of, I'm going to think about kilometer or mile scale blocks and think about where the fractures are connected and how they're running. And in this case, we're doing depths of imaging of a couple hundred feet for the smaller images and a little over 700 feet for the deeper images. And when we're looking at images like this, the red and the green are the start and the stop, and we're going to look 1/5 of the total line length below those lines and catch that picture and start thinking about where the dominant flow pathways are through that domain. Now they're kind of at funny angles. We had information already about some of the fracture flow paths we were looking for. Plus, we also had to get for the longer lines through trees and things and make decisions about what kind of pathway do you want to set up through those areas in clearing shrubs and trying to get through places that are easier to go. So if we look at a couple of these images, one of the little ones and one of the bigger ones, you can look at the change in resolution as you get a bit tighter on one of these things. But if you look at this fault here, that was found with airborne methods, and you could see that there was something changing through there. Surface mapping didn't find that fault, and then if we go in with this technique here, we can see that fault, we can see it dipping, and we drilled that, and you get into some issues when you've got targeting. So when you start targeting fractures with a driller, you're actually going to put them into really broken up rock. And we've had troubles at different sites of lost circulation and boreholes getting caught up as rubble is falling in on the drill bit. And so you try to warn your drillers that we're actually targeting, because they're not used to hitting targets where you're in the most destroyed chunk of rock on the site. And so dealing with some of those issues a priori, we now have drillers that are targeting, but they're pre-building their wells if they're going to be installing a well. They just pre-pack them, even if they're a 4 or 6 inch kind of recovery well. They pre-pack it because they know that some of these targets are going to be a problem relative to getting a well built in situ. When you get these smear versions, that's where we're at a different angle to it. So we had a nice cut across this fault, and we can see it really clearly. As you get these sort of smear features is when you're getting at an angle, some oblique angle relative to a fracture feature, and you're cutting part of it. And so working with those things, these guys and watching these blocks drop down as they go towards the spring, some of those features are clear and easy to interpret based on the known geology. And some of them, if you get a cut angle, you go, I'm not sure what that is, but if it's smeared out, you kind of go, well, we need to look at a different angle if we really want to see which way that thing's heading. So that's the sort of work you do on these images. You've got a 2D representation, and you've got to then extract what are we looking at and what should we target. If we make a map view of those sets of data, we have a big fault running through here that's done a nice job of causing some karstification along there. And so that target provides a good flow path down to the spring. And we can look at those sorts of features and tune in quite quickly to the important flow paths on a larger scale for a site. If we go to Australia, we've got to think about some other things. So Oklahoma, there was fresh water, very uniform. Here we go to Australia, and we're looking at the Great Artesian Basin in the distance there, sandstones. And then on the other side of the Kingston Fault in the foreground is a set of granites. And we've got to think about variations in salinity and what the fault might be doing. And so if we take a look at imaging across this fault, there's the fault, and as we come across it, up on the granites is very resistive. Over in the sandstones is very conductive. And this spring is built for a telegraph station because it was slightly fresher than the other springs in the area, and so provided better quality water. And the reason is it wasn't just from the Great Artesian Basin with the sandstones. There was also a flow path coming in from the granites. And so the set of sedimentary rocks and the fractures in the granite are combining to provide a mixed fluid chemistry at the spring. And you're trying to interpret, are we looking at an image that is affected by strong variation in salinity, or are we just looking at damaged zones in the rock? Now, when we go to contaminated sites, you also add microbes. And so you got to think about the pictures relative to the context you're in. If we look in the fault plane, now we're looking in the fault plane, and we can see that most of the fault plane is dominated by those fluids coming up through the granite, that the fault is flooded by the granitic fluids, and thus that spring is going to be nice. And the further you get into the granites, that fresher that water is going to be, and that's what they found historically as well. And then the Great Artesian Basin water is up at the top of the fault. So if you needed to drill a well in here and find the fresher fluids, you come up to the fault, drill deeper, and you get below the salty water, which is sort of a contrary thing to think about relative to saline issues. If we go to California, look at dry cleaners. So this is, they've got DNAPL and LNAPL, some PCE and some Stoddard solvent. Former dry cleaner, long since gone, but trying to deal with cleaning up a site. And they've got a stream, but it's an urban setting, and it's also a former mining district. So there's tunnels that were put underneath there. There were channels that were installed as part of the mining process. So you've got a whole set of natural fracture pathways with a bunch of anthropogenic pathways and alluvial pathways put on top of it. And then you start putting material in there and saying, which way did it go? When we look at this on an urban setting, a lot of your lines are defined by property access and then accessibility. You can go right through buildings and things like that, so long as you get permission to do it. What you're trying to do is get a straight line to be able to put electrodes in the ground. Your cable doesn't have to be a straight line, just your electrodes do. And so there's a number of lines that were put out there in order to get images that would define the conceptual model. And the consultant we worked with was very useful, and he says, you know, even if your images don't tell me anything, your targets you gave me and the stuff I found, I never would have drilled there. And there was flow paths here that were defined by mines, defined by the current alluvial aquifer, defined by the former alluvial aquifer, and then defined by the bedrock fractures. So in terms of that, we did 10 confirmation drilling locations, and every single one of them came out hot. And so we showed there was a lot of pathways, But in terms of trying to characterize this type of thing without an image, on these kinds of settings where you've got all this complexity, you go, well, drill a lot of holes. You go, okay, well, you're still in an urban setting. You're probably not drilling holes everywhere. But if you need to try to figure out the site and get it cleaned up, it's quite useful in an urban setting. People think, well, you got to do a straight line. That probably is not that easy. And it's like, well, if you got 20 years of figuring out how to put straight lines through urban areas, you figure that stuff out and you get it done, because it's actually easier in some ways than trying to get a drill rig in. You don't have the size of a drill rig and you don't have some of the noise issues. You just got some people putting some stakes in the ground and letting the electricity take the picture for you. So in terms of the data set, it looks ugly. And so there's a huge range of resistivity variation in a site like this when you have those kinds of products in this kind of setting. And so when you look at it, you go, I'm not sure where I would drill. It comes with experience of looking at the images, and it's very similar to being a seismic interpreter, except for you're doing it electrically. And so you're a seismic interpreter, or you interpret MRIs at the hospital. The simple ones are easy to show somebody. The more complicated ones, you go, that's messy. How do you do this? And you stare at these things for a long time, and you look at the numbers, you look at the shapes, you start looking at the gradients and these sorts of things. But you integrate all the other data in the site. So this is integrated with a whole set of site data that was collected before and after the electrical data, and you can look around and make decisions. So in terms of this target, this was a high resistivity target that coincided with a valley wall that we were looking at, and looked to be a bedrock fracture. So we defined the top of bedrock there in blue, defined this target to go after, and we got basically 1,300 micrograms per liter PCE down here at 65 feet. And you can see those targets where it's nice and resistive. You go, okay, I'm not weathered, and you can test the chemistry, and it wasn't weathered. But also it says, yeah, you've got some stuff at depth, but it's not all the way across the site. It's in these localized fractures. And so when it comes to remediation, you're not saying, okay, my entire site has gone down to 65 feet. You're saying my fracture is impacted and I've got to clean that one up. But you've also got data to support that you don't have to clean up everywhere at depth. And so you can find where these long-term problems are, but the treatment isn't necessarily pervasive across the site, because you're targeting what you're looking for, and then you can target the remediation. In terms of the values we found across the site, there was a number of different ones. So, in terms of basic normal hydro, there was that part of a plume. That was your basic sort of high levels coming out of the tanks. But then there was these other values around the site with flow paths that we could define, and we could figure out what they were caused by. But it's interesting in terms of trying to peel apart these sites just using wells. So lessons learned from that. When you look at a 3D bedrock site, and you've got metamorphics, and you've got all these things going on, and then you do some mining through it and stuff, it's a dog's breakfast of flow paths and biogeochemical reactions. There's a lot of stuff going on, and it's the way it is. And I had somebody tell me, yeah, we're kind of done with the simple plume sites. All we have are the messy plume sites. And I would say that's probably true. As a lot of the simple things have been done, and now we're dealing with pretty complicated sites, even if it's just a little dry cleaner. When you get to scan, you get the drilling targets that you can find the discrete flow paths and figure out where those are. And so when you go to remediate, you can make decisions based on, yeah, but I know I'm going right through here. And it sets up a different way to think about remediation. And you got to also set up sometimes different ways to think about drilling. In terms of porous media assumptions for complex bedrock sites, the ones I go into have typically been drilled based on porous media assumptions, and they're not cleaning up. And so it's showing you that approach, those principles aren't helping to get to where they need to be on a remedial outcome basis. The other thing that's useful on these sites is typically those fractures are going in strange directions. They're deeper than you think sometimes, but you end up with a really good volume reduction in the characterization volume or remedial volume that you have to deal with, because you're more focused. And so the remedial options become much more focused and cheaper because you know where you're going and you're going to go target a particular thing. So it sort of changes the way you work. As we go forward looking at fractures on these kinds of sites, you end up doing things similar to a seismic attribute analysis. And so looking at what angles things are, looking at whether you use the gradients or the resistivity or other parts of the data sets to characterize them. All that stuff works together and you end up down the same sort of road. So you, instead of having seismic interpreters doing an attribute analysis, you have electrical interpreters doing an attribute analysis to define pathways and whatnot. So it's similar sort of issue of you need to look at them for a while. And I teach people how to look at them, and it takes a little while to get good at reading the complicated ones. But you've got the values and their gradients and these sorts of things, and you can look at the basic geology, and you can put together a pretty good understanding. The other thing that we're doing a lot more of is using monitoring data. And so you can install a well, except for your well is going to be a cable stuck in at the surface, and we can watch those images change over time. And if you don't have a flow path, it's not changing over time. So on short term, we can watch remedial options like injection, or we can watch thermal remediation. But long-term site monitoring, we can watch where does the groundwater go as it's recharging, and if we have a reaction ongoing with bacteria, are they growing? And we can do those sort of long-term watches. So the electrical techniques, it's easier because we could digitize everything, and we can also take more people out of the equation over time, but we can also get a much denser and richer data set over time. So that's a little bit about fractures, and if you got questions, happy to answer them.
Hey, Todd, got a question here for you. Sometimes DNAPL goes quite deep at fractured bedrock sites. How deep have you imaged and found NAPL-related impacts?
We've gone 700 feet so far, and drilled and confirmed our DNAPL at 700 feet. So you can get quite deep, and typically when you got deep sites, they usually are in sort of bigger geologic structures. And so, you know, you're not looking for a tiny crack, you're looking for that pathway that's taking stuff downward. So thus far, going deeper hasn't been a limit. And you do have some resolution issues you got to confront, but thus far it hasn't limited us in targeting these kinds of sites.
Great, thank you. And a follow-up question, what would the depth limit for the technology be, and does that depend on the rock type?
So a friend of mine did a one-dimensional image in South Africa, and he did 1,200 kilometers long, so 1/5 the depth of that. You ended up being able to look at the crustal boundary. So the technique isn't the limit, it's more of stretching the cable out. So you got to go 5 times longer than your deep, but we've done urban hydrogeology to over 700 feet, looking, and so you're crossing a bunch of driveways with traffic control ramps, and you know, doing some crazy stuff, but you can catch those images and look around, and it saves you a huge amount of effort on drilling on those deeper sites.
Great answer, thank you. I've got a few more coming in here, so we'll just go through the list. Do you see this technology being used more for site characterization or as part of remedial design?
Yes. The single images we use a lot for characterization, but you know, I can see that in the future you would you know, maybe take a couple of borings and determine, nope, we're hot for whatever kind of NAPL we got to deal with, and we know we're going to go down the road of having to clean something up, and so then you install a couple cables at the site on a permanent basis, either electrodes in the ground or a full cable, and you start watching things while you're characterizing. And what you can do then is you can get a good understanding of preferential flow paths, reactions that are ongoing, and then you start remediating, and you've already got things installed to watch that happen. So it's going to be you know, somebody goes out to sample a wells, but they'll go out and sample a cable too, or a couple cables, and it's working with the data set, and it's similar to a doctor working with MRIs to manage a patient. And you're going to think about how are you going to do that in management of that patient. Do you want to have a second MRI, or do you want to have a time lapse of, what their brain's doing as you're doing brain surgery. Same thing for us, is we'll have these tools, but the electrical technique, once you get things installed, and installing an electrical well, which is installing a cable at surface, and it costs similar to what you do for putting a piece of PVC in the ground, but now you're going to keep collecting thousands of data points every time, and you're able to watch the changes between them. So we're doing that on that EPA site I showed you with the city of Ada, and so we're getting some of those permanent ones installed. We're also doing that over an NREX segmented horizontal well, and we're defining the well hydraulics electrically, and so we're watching as we squirt into different areas and watch how it transitions from one zone to the next in a vertically faulted zone. So as we get sort of better at this bag of tricks, we've gotten better in the last 20 years at just reading the images and figuring out how to best target them. But now we're going to be getting much better at managing temporal changes and watching groundwater move.
Thanks, Todd. So, to answer succinctly, yes, we are useful for both characterization and part of remedial design. So, as Todd said, there's different ways we can approach problems, and we're kind of a great tool to have anywhere along the way. Alrighty, well, Todd, next question here. Can you talk to the specifics of the field methods and data analysis? Let's see, they said they found that resistivity is limited in a highly karst area with clay regolith.
Yeah, so the GeoTrax technique we developed, and the reason I got licensed out of the university, was we increased the sensitivity by an order of magnitude. So your ability to see underneath the clay went up by about a factor of 10. And so we've imaged saline mud flats where we're watching fresh water coming up through salt. And we've imaged on different kinds of geology around the world. We do a lot of karst work for impacts, and then we do karst work for foundation management for folks in saline areas with karst that are trying to put like oil rigs up and things. And they need to be able to see those features to be able to do foundation stability. But it's functionally the modifications we did in the GeoTrax algorithms to make that image good enough to be able to poke underneath clays and look around.
Yep, thank you. Let's see, next question. Can you correlate data sets to borehole imaging data?
You can, and it depends on what you have for logging data. If you've got like electrical logs, that's going to be basically a higher resolution than what our image is, so you'll get kind of the sharper parts of some of our images. If you're logging them relative to like an optical logging tool, you can see where that fracture's at and then look and see what you get on the image. And so that's sometimes helpful to map out the fractures, because sometimes you won't get like that fault where it's just a big conductive feature or something. Sometimes you'll get kicks in the resistivity and you go, oh, okay, we're looking for that kick and we're translating it across. So similar to the seismic attribute analysis, once you find your attribute from the well log, you can then look at how that tracks through the image data set.
Great. Next question. Let's see. How implementable is it in extremely rural or remote areas?
You can drive a truck there, you can implement it.
Or UTV even.
Yeah. So commercially, we do a lot of middle of nowhere sites, and that would be middle of nowhere that, hey, it's hard to get a rig out there, we want to look around, or they got to drill deep in the middle of nowhere, in which case they go, hey, we're going to spend a lot of money, let's get some images first. Or like island environments where you go, hey, I got to get a drill rig here, but I don't even know where we're starting, let's get some images, because all you guys have to do is come in with some wires and stakes. So we typically go around with a pickup truck and a trailer that has all the traffic control and survey gear and all that kind of stuff in it. But we've been all over the US, from the middle of the busiest cities through as remote and rural as you would like.
Very good. And see, I'm going to hit you with two at once here. So we've got, what is the general cost per data array, and how are the effects of overhead or underground power lines avoided?
So general cost is like an image is like a $10,000 kind of thing. So it's like getting a well installed, except for you're getting 2,000 data points instead of one. And then, so a typical site, if you took like 10 images, is, on the order of magnitude of 100,000, but people will say, well, I've got a bigger site, and you go, well, you're going to spend more money as you take more images. So, shorter lines are, more towards the 10,000, and longer lines are more towards the 20,000. And then as you take lots of lines, you change cost depending on what's involved relative to, are we going through buildings, are we doing this and that. In terms of avoiding utilities and things, for electric utilities, the system collects and it knows that there's 60 hertz power out there. So you just make sure you avoid that and don't use that as part of a signal. And so we've never had any problem with overhead or buried power lines. The other one is thinking about like other metal utilities, and most of them are coded now. So most of them aren't, it's not a great utility detector because most of the utilities are coded and they don't show up. But like a bare old water line that hasn't rusted a lot, which is a hard combo to get, and some gas lines that are uncoded will show up. And so you just work with that, and we've worked with it on hundreds of sites, and we don't get, we can see some utilities, but it's not a problem relative to doing interpretations around them. The other thing now, in terms of one thing that will get us, is around a transformer pad, because people have DNAPL problems on transformers. Right around a transformer, a lot of times they'll put in a grounding grid and they'll basically mesh the whole thing electrically. I can't see under that because essentially you just wired up the whole surface. And so if you put stakes there, all you're doing is connecting them with a big chunk of wire. So a grounding grid I can't get through.
Great. Okay. Next question. Would you recommend use of this technology at a site with NAPL distribution, with complicated fracture network?
Sure. And your other technology choices, drilling holes where you don't know where the fractures are at. So having an image and seeing where the fractures are, it doesn't make the problem simple. I've looked at a bunch of different fractured sites, and you go, wow, these are really messy, and I've got 20,000 or 50,000 data points to work with, and this thing is messy. And you go, well, let's only collect 3 data points, and the site will be much better. So it's been tested, it's done it a lot, but it doesn't make the site simple, right? So having lots of data shows you the complexity, but it doesn't, turn the site into, oh, well, now we're back to a simple plume. It's like, no, you're in a fractured domain where they also threw some mines through it, they also threw some channels across it, and then you've got the other parts of the geology going on, and then you have bioreactions happening. So good luck. But in terms of what our job is, people say, I've just got a dry cleaner site, or I've just got a gas station. And it's like, you've got fairly complicated compounds or families of compounds with some fairly complicated reactions in a really complicated geology. Just because we have a, quote, simple site of conceptually simple, our job isn't easy, but this makes it much more tractable to be able to look around and be able to target things.
Yeah, absolutely. Great answer. Thank you. Last one we've got here. Is there extra cost to image through Bedrock like there would be to drill through it, or does the imaging technology not care what it's imaging through?
The electrons do not put a surcharge on that. So if you want to send an electron through sand or through granite or through anything else, the electron doesn't hike up the cost. So he just flows through there and gives us the data.
Great, thanks, Todd. Well, if we don't have any more questions, I think we can call it a wrap. So we really appreciate everybody's time and interest today, and hope everyone a good and safe rest of their week.
Thanks, folks. Much appreciated.
Thanks, Todd.